podcast is brought to you by LMU Munich.
Relativistic physics. In fact, most of the interest in this subject comes from the experiment done with the realization of something called fermions at unitarity. So we are going to explain what fermions at unitarity is, and then we'll try to understand the more formal aspect of this system, fermions at unitarity. So, in fact, the system called fermions at unitarity can be explained at the purely quantum mechanical level. So let me start by just considering the simplest quantum mechanical problem of two particles interacting through a central potential. So if you have two particles interacting with a potential, and for simplicity, let me assume that to be just a square wave potential. And it's attractive, let's assume. So here is 0, the potential is negative when r is less than some r naught, and the depth of the potential is minus v naught. Okay. Then we know that if the potential is deep enough, we might have a bound state, or if it is very deep, then we have more than one bound state. If the potential is shallow, then there is no bound state, right? And there is a critical value of the depth where you would have you would start to have a bound state. You would have the single bound state at 0 energy, and that happened at v naught equal to some number that I'm not going to write down, divided by m r naught square. So there is a critical value of the potential depth where you start to have one single bound state. Okay. Any questions so far? I hope not. Right? Everything should be clear. Now let me take the following limit in this problem, namely the limit when r naught goes to 0. So the potential becomes more and more, the interaction becomes more and more contact-like interaction, but I will keep v naught time r naught square critical. See, this is v naught r naught square. If you keep it fixed, then if you have a 0 energy bound state in the beginning, when you rescale both r naught and v naught, you will always have a 0 energy bound state. Okay. So this is the situation where the potential is point-like, but the interaction is strong enough so that the two-body problem is non-trivial. Right. Okay, so this, in fact, this is called. So this interaction is called zero range infinite scattering length. Interaction. I'm just going to introduce several terminology that is frequently used in this subject. Zero range means r naught going to 0. Infinite scattering length means resonance scattering, and we have a resonance at 0 energy. The bound state is at 0 energy. We have a resonance at 0 energy. And experimentally, people have managed to create such a system where I will not going to describe how they do that. I'm just draw a picture. Basically, you have atoms that are very far away from each other. So the system is dilute. The interparticle distance is much bigger than the size of the atoms. But using the external magnetic field, you can fine-tune the interaction between these particles so that effectively you have a potential of interaction where the if you take two particles, they would form. You can you take a two particle problem, they would have a zero energy bound state. Now we are going to talk about the case where these particles are fermions with spin 1/2. In other words, we are going to assume there is a spin degree of freedom. When these particles are fermionic, then what I said about the bound state at zero energy applies only when the one particle is spin up and the other is spin down. In this case, the wave function can be an S wave. If the two particles are both have the same spin, then Pauli principle tell you that the wave function should be zero when the two particles coincide, and the effect of interaction can be neglected. Okay, so in the case of we are going to consider fermions with spin 1/2 with this kind of interaction. Okay, so far everything we describe everything in terms of particle interacting through some potential, just a very standard quantum mechanical problem. Let me reformulate this problem in such a way that we will see the universal aspect of it. That we will see that this problem is not dependent on the potential. Three dimension, yeah. So it's in physical, it's the correct number of dimension. 3 spatial dimension one time. Okay. The most non-trivial problem will be the problem of many body in say you put many of these particles in a box and you ask the question about the ground state energy and the ground state properties. But for simplicity, let me start with just 2 particles again and write down the Schrödinger equations. So frequently I will set the mass of the particle to 1, in particular here. Okay, plus V of x minus y times psi is equal to E psi. Okay. So this wave function is a function of x and y. Of course, you know that you can factor out this wave function into the center of mass motion and the relative motion, and so for the relative motion the equation becomes something like minus gradient with respect to r, where r is this, is equal to E psi. Okay. Now we are interested in the limit where the potential range is 0. So most of the time r will be going to be bigger than r0, okay? And that means the potential term can be neglected, and you have just the Laplace operator on the left-hand side. And now let us consider, so we take this to 0, so effectively r is always, for any value of r, the wave functions have to satisfy this condition. Now, if r is small, small here means still bigger than this r0, but r0 is really very small. If r is small, then the right-hand side of this equation can be neglected, so you have just the Poisson equation. At short distances, the wave function satisfies the Poisson equation. which has, we know, this equation has two solutions, psi equal 1 and psi equal, it can be a linear combination of two solutions. Let me call it A plus B over R. Right. Usually when we think about the solution to the Schrödinger equation, typically we impose the boundary condition that it is the wave function is regular when the coordinates of the two particles coincide with each other. However, the case of this fermion, of this particle interacting with the short-range potential fine-tuned to resonance can be thought of as imposing a different kind of boundary condition for the wave function. Namely, we impose the boundary condition that psi has to be proportional to 1 over r. Okay? Psi of r has to be equal to some constant divided by r plus 0 and then plus something that is proportional to r. Now let's think about that. In order to, we have a second order differential equation and there are two solutions. We can impose the boundary condition at infinity that counts as one boundary condition. We have to impose another boundary condition at r equals 0 to completely specify the solution. That condition can be thought of as the ratio between these two coefficients, A and B. Okay? And there are two special choices of the boundary condition that respect scale invariance. One is when we impose the condition that the wave function goes to constant, and the other one is when the wave function goes to 1 over r without any constant. Any question? Please. Okay. A more general boundary condition would be psi of r equal constant time 1 over r minus 1 over a plus some value, some correction that is of order r. That 1 over that value a here in the theory of low energy scattering is called the scattering length. Okay. And so that explains another terminology that is used, infinite scattering length. In other words, mathematically what we are saying here is that we define the Hilbert space of our theory to consist of only wave functions which satisfy a certain boundary condition. The problem, therefore, is that is formulated as follows. So the problem of unitarity fermions is the problem of solving the Schrödinger equation that is just a trivial looks like this. So here the wave function depends on the coordinate xi, x1 go to xn, y1 go to ym, where here I separated the coordinates of spin up and spin down particles. With a boundary condition that psi whenever x yj, whenever xi approaches yj, has to behave like a constant, divide some function of other coordinate divided by xi minus yj plus correction that start at the linear order of xi minus yj. Yes? Okay. So xi go to yj. Here is some constant divided by okay. So formulated in this way, the problem, the non-triviality of the problem is not in the Hamiltonian. The Hamiltonian is just the Hamiltonian of the sum of kinetic energies, but the non-triviality comes from the boundary condition that one imposes on the wave function. And this problem, even the simplest, in most cases, this Schrödinger equation cannot be solved exactly. Say if you have the situation as people have in the experiment, roughly speaking, you put 10,000, 100,000 of these particles in a box and ask the question about the ground state energy, it cannot be solved. If these particles satisfied, if the wave function satisfied a different boundary condition, namely that when the two coordinates go to each other, the wave function is regular, then we would have just a free non-interacting gas, and you know everything about this system. With this boundary condition, most of the time you cannot find the exact solution to the Schrödinger equation.
What's the boundary condition for xi versus xj?
That is the usual boundary condition. When these two coordinates approach each other, the wave function should be at least in the relative p wave. So it has to be like x minus, it has to be proportional to xi minus xj. The wave function vanishes when the two coordinates go to each other. There is one particular case where the problem can be solved exactly, and let me just mention it here. That is when we have two particles in a harmonic potential interacting with this potential, with this boundary condition. So imagine that we have an isotropic harmonic potential. That means that we add to the Hamiltonian. The Hamiltonian is kinetic energy plus x squared over 2 plus y squared over 2. Okay, so let me set the frequency of the harmonic potential to be 1. And our task is to find the solution to the Schrödinger equation, in particular the ground state of the system. So in the case of non-interacting particles, we have one fermion with spin up, another with spin down. They can be both in the ground state. The ground state wave function is just e to minus x squared plus y squared divided by 2. So now that in the case where we impose this non-trivial boundary condition, the Schrödinger equation also allows exact solution. Then the exact solution is just this Gaussian shape divided by x minus y, absolute value of x minus y. One can, it's rather straightforward to check that this is the solution to the Schrödinger equation, and one can also check that it satisfies the boundary condition. When x goes to y, you can see here that the wave function becomes singular. You need to check additionally that the first correction is 0 and only the next leading correction is non-zero. The energy of the ground state here is equal to 2. Okay? That can be compared with the energy of the ground state when particles are not interacting. When you have non-interacting, this is the interacting case. In the case of non-interacting particles, the energy of the ground state is equal to not to 2 but equal to 3, because each of the particles would have energy equal 3/2 times the oscillator frequency, which is 1 here. So 3 is equal 3/2 plus 3/2. So one can interpret this as that you have two particles, but they interact through attractive interaction. So the potential, can associate this -1 as the shift in the energy that is due to the fact that the particles interact with each other. Okay. So we will interpret this formula a little bit later in terms of the there is another interpretation of the energies of a system of particles in the harmonic potential. Okay. This E is the energy of the ground state. The ground state energy of two non-interacting particles in a harmonic potential is equal to 3. Each particle has energy 3/2, and they have different spin, so they can be in the same state, and so that energy is 3.
I'm confused because naively there seems to be order 1 term when you expand in distance.
This
which depends on the cosine theta.
order 1 term when you expand.
When you expand it in the distance between x and y,
Mm-hmm.
there is an order 1 term which depends on the angle between x and y.
No, there is it turned out that that is not you expand it times e to x plus y square over 2, right? So yeah, so the order 1 term, order 1 term decouple. There is only this order -1 and order 1 term. On the 0 term vanishes. Now let me briefly tell you how to write down quantum field theory. How to write this theory in the Lagrangian form. In the Lagrangian form, we can do the following. Let us introduce a fermionic field psi that has been indexed sigma. Right? So we have to sum over sigma I dt psi minus psi square over 2. That is just a free non-relativistic particles in the second quantized form. That is the Lagrangian. Okay, it's first derivative in time because the particles are non-relativistic. Omega equal p squared. Then we know that introducing the attraction can be done through, let's formally write it as the contact interaction between spin 1 and spin 2. Okay. So that formally is the Lagrangian of fermions with contact interaction. Now we have to understand what does it mean, the fine-tuning of the depth of the potential. What does it mean in the Lagrangian formalism? And to do that, to understand that, let me rewrite this in a slightly different way. Rewrite this Lagrangian in slightly different way using just a Gaussian trick. That is, instead of having 4 body interaction, I will introduce an auxiliary field phi. And introduce this phi vector phi divided by C naught. If you integrate over C naught, then you will see the four Fermi interaction appearing again. Phi appears in the Lagrangian only quadratically, so that can be done exactly, the integration over phi. Now, but now I want to look at phi as a dynamical field instead of as an auxiliary field. Let me try to understand what is the propagator of this phi. So clearly, at the bare level, the propagator of phi comes entirely from the phi decker phi over C naught term. So we write the usual expression for the full propagator. The inverse of the full propagator is the inverse of the bare propagator plus the self-energy. So this one is C naught, okay? And we have to draw some diagram for the self-energy. So the diagram, the first diagram you draw is the following. Is phi coming here, split into two particles that would move in the same direction and then combine into a phi again. That is the simplest diagram that contributes to the self-energy. Yeah?
What's the meaning of a propagator for a non-dynamical field?
It is a constant, so it's at the bare level. This non-dynamical field has the propagator that doesn't have any pole. It's just a constant. However, we will see that the kinetic term, a non-trivial kinetic term for phi is generated once if you integrate over psi. Okay, so in the field phi that was introduced as a mathematical trick to rewrite the four Fermi interaction now we'll have a physical meaning of a dynamical degree of freedom. That we will see that appearing. This is the operator that annihilates the particle. So you can think about this as a second quantized formulation of quantum mechanics. Quantum mechanics can be rewritten as a path integral, and that when you write the path integral, this you have to integrate the exponents of the action with respect to this fermionic and bosonic field. Okay. It is equivalent to the Schrödinger equation, but it is a nice way to do the Schrödinger equation. Okay. Now let's compute this diagram. At least we can write it down. So here, if the incoming momentum is q, then here you have p, say q minus p over 2, and then here you have q plus p over 2. And I just write it down like this. E4 pi 2 p to the fourth 1 over q naught minus p naught square p naught over 2 plus minus a half q minus p over 2 square, and there is some I epsilon that is important to get the result right, but I won't write it down. Something like this. So something like this is the self-energy. So the self-energy that is here is equal to this up to some factor of I or plus minus 1. You can count the dimension and convince yourself that the integral is divergent. In counting the dimension, we have to remember that we are in the non-relativistic world. So the P0 is counted as momentum square. The energy is momentum square. So this one has the dimension of momentum to the 5th power, not p to the 4th power. The measure of the integral is integral over p to the 5. Here we have in the denominator p to the 4th. And so if you compute the one loop graph, you will see that it's divergent logarithmically as a function of the it is divergent. It is linearly divergent as a function of the cutoff. And that can be already seen by counting in the original theory. In the original theory, before we introduce this interaction, you can count the dimension of all field and and convince yourself that this 4 Fermi coupling, 4 Fermi interaction is irrelevant in 3 plus 1 dimension. Okay. You can do that quickly here. So the Lagrangian again is this et minus phi square psi plus c naught psi decker psi. Okay. The Lagrangian density should have dimension 5 because the action which is integral over dt dx is dimensionless. So this one has dimension 5 in momentum. That means that the dimension of psi is equal to 3/2. Okay, so 3/2 plus 3/2 is 3 plus 2 will be equal to 5. But that means that this 4 Fermi term has dimension 6 and the dimension of C naught is equal to -1. And usually you get diverging loop graphs when you deal with a theory with which is not non-renormalizable. Okay. Usually in this case there are the theory became ill-defined. In this non-relativistic case, you can prove rigorously that this is the only graph that contributes to the self-energy of the boson field phi. And that comes from the retarded nature of the propagator. The propagator in non-relativistic theory is fully retarded. It has pole only on one side of the complex plane. And so if you draw some other diagram, you will easily convince that you cannot have all the arrows going forward in time. This is the only diagrams that would be non-zero if you require that all the fermion propagator has to go in the same direction in time. Okay, so this is actually the exact calculation. Still divergent. We can compute also the leading the non-divergent piece that came out to be something like Q naught Q square over 4 minus Q naught with some number in front. Now recall that the full propagator is the sum, the full inverse propagator is the sum of this inverse bare propagator and the self-energy. Self-energy is divergent, but that divergence can be absorbed into the coefficient C naught. So if we make sure that the sum of C naught and this lambda is finite, then we have a finite propagator for the bosonic field. That is what fine-tuning means. The fine-tuning of the potential in quantum mechanics is basically the fine-tuning of this coefficient C naught and the cutoff. In particular, if we make C naught and lambda combine to 0, so that this term and this term cancel each other, that situation corresponds to the zero energy resonance that I've been talking about. You can see it here. The propagator of phi start to have a branch cut at zero energy when the momentum total incoming momentum of the two particles is 0. That corresponds to a resonance at zero energy. So the theory of fermion at unitarity can be summarized as this Lagrangian with a fine-tuned coefficient C naught. Okay, C naught has to be proportional to the cutoff. That is because if we would compute this integral not with the momentum cutoff, but we compute this integral using dimensional regularization, for example, then the linear divergence doesn't appear at all. You can, it's a property of dimensional regularization that anything that is linearly divergent is set to 0. So in dimensional regularization, actually this term doesn't appear at all. If you consistently use Dirac, then the Lagrangian of fermions at unitarity consists of only of this piece and this piece. All the phi here would appear as just some non-dynamical field that would get its kinetic term after you compute this loop integral. Any question?
So should C naught minus 1 be 1 over C naught?
Should it be? Yes, it's a C naught minus 1. Thanks. C naught minus 1. C naught should go to 0. In fact, you can see that at the quantum mechanical level as well. The depth of the potential is proportional to R1 over R naught square. You integrate this potential over space, the total integral is R naught and goes to 0. Okay, now I'm going to talk about the symmetries of this problem. It is a it is something that would turn out to be formally quite interesting, and it probably will be useful if we want to understand the holographic realization of this unitarity fermions. But let me say right away that right now we don't have a holographic realization of these fermions at unitarity. We have only the realization of systems that have the same symmetry. For non-relativistic theory, there is no Lorentz invariance, but we have so I'm going to talk about Galilean invariance first. Lorentz invariance is replaced by Galilean invariance. Galilean invariance consists of usual time translation. T goes to T plus A, or spatial translation. So this one is related to the conserved Hamiltonian energy. This one is related to the conserved momentum. There is also rotation that is related to the conservation of angular momentum. The Galilean invariance is the following transformation. T goes to T, and X goes to X minus Vt. Let's call this transformation K. K should have an index I that runs from 1 to 3 because the vector V, the velocity, is a vector. Okay. Now, this Galilean invariance does not generate conserved charge, and that's because the K has non-trivial commutators with the Hamiltonian. In particular, if you compute the commutator of K with H, you can convince yourself that it's proportional to P. On the other hand, you can check that the action of the theory is invariant with respect to this transformation. In particular, that the physical one of the physical consequence of Galilean invariance is that if you have a solution to the Schrödinger equation, you can boost it and get another solution. You can from one solution psi t of x, you can get another solution that looks like something like this. Psi tilde t of x equal e to minus I m v dot x plus I m v squared over 2t psi of t x minus vt. And you can put it into the Schrödinger equation and convince yourself that it is a solution. So Galilean invariance does not correspond to a conserved charge, but it has physical consequences like this. Now, for interacting particle as well. You can see that, well, in the case of unitarity fermions, all you have to do is to check that the Hamiltonian, the Schrödinger equation is satisfied. The Schrödinger equation has only kinetic energy, doesn't have any potential energy. Also, you have to check that the boundary condition is satisfied. In fact, this is the Galilean invariance is there even if you have a potential between the particles. But this is not the properties that there are additional symmetries of the fermions at unitarity that makes this problem very much nicer than a general problem. You have scale invariance. Scale invariance here means rescaling both space and time, but space has to translate, has to dilate twice faster than, the time has to dilate twice faster than space. So in other words, if I have a solution to the Schrödinger equation, I can generate another one by just appropriately rescaling space and time. If you want this wave function to be normalized to 1, then you also have to add a factor like, I think like lambda to the power of 3/2. Yeah. That will be a new solution. And that's obviously the property of free particles, but it is also a property of fermions at unitarity. It is scale invariant, so you can say that theory doesn't have any dimensionful scale, so this one has to be a solution. The size of the potential goes to 0. The energy of the bound state is 0, so there is no intrinsic scale in the problem. But the most non-trivial symmetry is the following one. T goes to T over 1 minus lambda T. X goes to X over 1 minus lambda T. Let me call that transformation C. It's the single proper conformal transformation in the non-relativistic case. The mass is, in non-relativistic case, can be safely set to 1. It can be thought of as just a parameter that doesn't have any dimension. We associate dimension with P, momentum, and the dimension with energy, say omega. Okay? Omega now is equal to P squared in the unit system where the mass of the particle is set to 1. So that is the counting. Mass doesn't appear, mass can be just set to 1 in non-relativistic case and doesn't carry any dimension. So in the case of that we are going to consider particles, is not going to, there is no particle, there is no, the flavor of the particle doesn't change. The particle just come in and then scatter, go out. Okay, this C, it is rather a non-trivial thing to check, that you can generate solutions of Schrödinger equation, one parameter solution parameterized by this lambda using this transformation. So there are two parts of this check. First, you check the Schrödinger equation is satisfied. Another check that is rather which we can do here is to check that the boundary values, the boundary condition on the wave function is satisfied. You see that in this transformation, x is multiplied by some factor that depends on time, but that doesn't mess up the boundary condition of the wave function that is formulated at equal time, right? This wave function time is assumed to be there is just one time, so this this 1 over x minus y asymptotics remains unchanged when you do this transformation. So this whole there is a group of symmetry of this system that is much larger than the typical symmetry of the non-relativistic system. It has this D and it has C. And you can compute the algebra that is formed by these operators. It can be summarized in the following way. So I will ignore this. The commutator of angular momentum with any operator is rather trivial, determined by the index, by the SO3 structure of the operator. So I will plot here I will plot here the remaining operators. So here is P, here is H, here is K, here is let me see, here should be C, here should be D, and here should be N. There is one more that I forgot to mention. That is just the trivial change of the phase of the operator. If I have a psi, a solution, I can multiply it to a arbitrary phase, and that operator, let me call N. That is the conserved number of particles that generate the phase rotation of the wave function. Okay, so here I have the remaining all the operator except this Mij is drawn here. And let me tell you how the commutator works. If you want to compute the commutator of P of K, you take this vector, sum them together, and you get N. So you can check actually that Pi Kj is equal to minus I delta Ij N, for example, something like that. If the sum of the two vectors goes beyond this table, then the commutator is 0. In particular, the commutator of N with anything is 0. N is the central charge of this algebra. Sometimes this algebra is called the Schrödinger algebra. It is not, I think it is because it is a symmetry of the free Schrödinger equation. And another properties of this algebra is that C, D, and H form a closed subalgebra. And you can check that C, D, and H form SO 2,1 subalgebra of the Schrödinger algebra. Okay. Any question? So So the structure of this algebra is very similar, but similar to the conformal group in non-relativistic physics. There is some distinction. Most notable distinction is that there is only one conformal, proper conformal operator that we call here C. So the restriction from conformal symmetry is typically less severe than the restriction on from the relativistic conformal symmetry. Yes.
How would that operator M fit into this algebra?
This M is what is the
Rotations.
the M? So if you have, for example, you want to compute the commutator of M with a scalar operator, you can say it's always 0 because a scalar is invariant under rotation. If you want to compute, say, the commutator of M with a vector, then it's you just say that the vector rotates by rotation. So the commutator is determined by the transformation property of the operator under rotation. So it's nothing special there that happened. Okay, so there is a generalization of the notion of conformal field theories into non-relativistic physics. Let's tentatively call this class of theories the non-relativistic conformal field theories. So unitarity fermions can be thought of as one of these non-relativistic conformal field theories. So, but let's talk about the non-relativistic conformal field theories in slightly a more general way first, and then specialize onto non-relativistic theories. So, as usually in quantum field theory, we have notion of local operators. We have operator that depends on time and space. So here, let me write it as T and X. Okay. For example, the operator psi or the operator phi would be this operator in the non-relativistic conformal theories. We can define the dimension of operator by looking at how the operator commute with with dilatation. So when we do dilatation, there is one point that is the origin that remains unchanged. If you compute the commutator of this operator O taken at 0, then the commutator will be the dimension of this operator times itself. So for example, the dimension of psi is equal to 3/2. You can also convince yourself that from the algebra, the dimension of k is -1, and the dimension of momentum is +1. Okay, momentum has dimension +1. That means that if we have an operator with dimension delta, say I draw here a diagram like this. This is a dimension, and you commute with P, you raise the dimension by 1 unit. In other words, commuting an operator with P would mean taking the first derivative of the operator with respect to space. So the derivative, of course, raise the dimension by 1, and you can see that at the level of the algebra, that if you define the commutator this way, then the dimension of the P commute with O is equal to the dimension of O plus 1. Time derivative would raise the dimension by 2. So here's the commutator of H and O would have dimension delta plus 1 here, delta plus 2. Okay. A non-trivial thing happens if you try to commute this O with the operator of Galilean boost or this proper conformal transformation. You can check that if you, from these relations, if you take the commutator of the operator with K, you get an operator with dimension delta minus 1. And if you commute the same operator with the proper conformal transformation, you get delta minus 2. So if you look at this picture, and then assume that then from one operator you can create a ladder. You can climb up by taking derivative or commuting the operator with momentum and Hamiltonian, or you can climb down the ladder by commuting the operator with Galilean boost or proper conformal transformation. But if we assume that there is a bottom of the ladder, then there must be a last rung in the ladder. There is a class of operators which commute at 0 at the origin with both K and C. So there is a class that is called primary operator. Which commute both with C and with Ki. So right now I'm introducing this class of operators very formally by just thinking about how basically thinking about the representation of the Schrödinger algebra.
Are you saying that there is state operator correspondence in non-relativistic case?
In non-relativistic case, there is the following correspondence that I'm going to describe. The correspondence in non-relativistic case is that with a primary operator, O, if O is a primary operator, O is primary, I can put that in correspondence with the eigenstate of a system of particles in harmonic potential. So before attempting to prove that, I'm going to just demonstrate in examples how this correspondence works. Say there is one primary operator in the theory of element of fermions, that is this operator psi that annihilate a fermion. Okay. If psi has dimension 3/2, as we have counted before, and if you have one particle in a harmonic potential, the ground state of one particle has energy 3 half. So the dimension of the operator map into the energy of some system in harmonic potential. A non-trivial example is when you take this operator phi. You can ask, what is the dimension of phi? Recall that we have seen that there is an exact solution to the problem of two particles in a harmonic potential, even when they are interacting with this fine-tuned interaction. The energy of the ground state there is equal to 2. Okay? So from this operator state correspondence, we conclude that there's the dimension of this operator phi has to be equal to 2. Okay, let's check that. Let's check that the dimension of phi is equal to 2. We know the propagator of phi. From the propagator, it's easy to get the dimension. So the propagator of phi x, phi 0, is the Fourier transform for p e to I omega e p dot x time its propagator, and the propagator of phi, recall, is the inverse of a square root of p square over 4m minus p naught to minus 1. We have computed this propagator by computing the one loop graph, and then we say that this one loop graph has linear divergence. The linear divergence is cancelled out by the bare propagator. The remaining piece is linear in momentum but finite, and its inverse is the propagator. So here we see there is an integral that can be associated dimension 5. This one is dimension 1. So this is like roughly speaking 1 over x to the power of 4. In fact, it is not 1 over x to the power of 4 because there is a asymmetry between time and space. But by dimensionality, this has dimension 4. That means the dimension of phi has to be equal to 2. Exactly the same value of the energy of two particles in the harmonic potential. So in order to prove this correspondence, we have to know the following fact. In order to prove this correspondence, there is one additional thing we have to know, is that this operator of the proper conformal transformation can be expressed in terms of the elementary operator as in this formula. So the Hamiltonian in the harmonic oscillator is equal to Hamiltonian in free space plus basically plus C. Okay. And now this correspondence can be proven algebraically. It's proven by doing the following thing. We can prove this correspondence algebraically by constructing explicitly the a solution to the Schrödinger equation. So if we have an operator O, say O can be psi or phi or some general any primary operator, we can act that creation operator in the vacuum and then create a state, but this state will have all particles located in the origin, we evolve this system with a Hamiltonian in imaginary time, and that will be equivalent to letting this particle diffuses from origin. The Schrödinger equation in imaginary time is a diffusion equation. So roughly speaking, here we'll get a state whose wave function has a wave packet form. Okay. And this one we can show using the commutator of the Schrödinger algebra to be the eigenstate of the Hamiltonian H plus C. But this is the harmonic potential Hamiltonian. The harmonic potential, putting the system in harmonic potential correspond to adding C into the Hamiltonian.
You write e to the minus h.
Yeah.
No coefficient. E to the minus.
If we can in principle add some coefficient omega here, and one can show that this is the solution to the equation h plus omega square c equal to omega delta. So we can construct the wave function of harmonic potential with the frequency omega. Okay. So you can read about this in a paper that Yusuke Nishida and I wrote recently. Okay, now I want to mention some very recent development in the theory of unitarity fermions. That has this development is recent, and a lot of things are still not very is still, I think, is in are in the underdeveloped stage. That is the question about operator product expansion in the non-relativistic conformal field theories. If we take two operators separated by in space and time, one can expect to be able to write the this product as sum over local operators. But in the non-relativistic limit, in the non-relativistic case, the coefficient depends on t and x, and scale invariants only tell us that we know this coefficient should be delta 1 plus delta 2 minus delta n times some functions of x squared over t. And in general, this function can be a non-trivial function of x squared over t. So this is still under investigation. What is the structure, general structure of a unit of the operator product expansion in the theory of unitarity fermions? And thinking about that has actually enabled one to reinterpret some findings in the theories of unitarity fermions in the quantum in the language of quantum field theories. So, for example, this operator product expansion is very useful if we want to investigate structure of the unitarity fermions at short distances. Say the equivalent, the analogy here is with the deep inelastic scattering. In when you study the structure of a proton at very short distances, you do a deep inelastic experiment when you scatter a virtual photon onto a proton, and you can reformulate the problem in terms of the operator product expansion. You compute the operator product of two currents and then express that in terms of the local fields, and you want to parameterize the expectation value of these local fields in the proton state. So here you can see if you Fourier transform that, then the most important in the limit when the momentum and frequency goes to infinity, the most important contribution are those who comes from operator with lowest dimension, because the Fourier transform of this object is going to decay very quickly as omega and q goes to infinity. So in order to characterize a state, you have to know the expectation value of typically a finite number of operators. For example, you want to know the average density. So psi decker psi would give you the density. So that operator has dimension 3. Or you want to know the expectation value of phi decker phi. That operator has dimension 4. These are the lowest, the two scalar operators with lowest dimension and that are neutral under charge rotation. So in many cases, the second one would contribute to the physical quantities. So this is the characteristic of a non-perturbative state, of any state. For example, you put a system in a box, you can ask what is the expectation value of that operator, and that is called the Tan's parameter. Which was introduced by Tan using purely quantum mechanical language. But we can understand that parameter that at first looks very mysterious as an expectation value of a local operator in the non-relativistic conformal field theory. Any question? Okay, and this parameter is important for various physical quantities. For example, if you compute correlation function of density correlation function at short distances, that operator appears. Okay, so now in the last few, yes? So the operator product expansion is a statement about operators. It doesn't know about this. After having the operator product expansion, you can take the average of both sides with respect to any state, and that would still hold. The utility of that comes when you take this separation between the operators to be much smaller than the interparticle distance. And then in this series, only the first few terms are important. The higher terms with operator with higher dimension decays very quickly. Okay, so now I'm going to mention very briefly how one can imagine such a theory be realized holographically. the ADS-CFT correspondence was one of the first evidences for this ADS-CFT correspondence is the matching of the symmetries between the symmetry of conformal field theory and the isometry of ADS space. So one can ask whether there is a space-time with isometry of the Schrödinger group. Okay, so these are the symmetries of the group that is spanned by these operators. So now that one can write down such a space-time, and the way to do that is to notice the following thing, that the usual conformal group can be thought of as the symmetry of the Klein-Gordon equation, while the Schrödinger group is a group of symmetry of the Schrödinger equation. So let me write it down like this. So Im minus psi. Okay. However, there is we can go from the conformal group, from the Klein-Gordon equation into this equation by going first to the light cone and then restrict the form of the operators of the wave function to have one light cone momentum equal to a fixed number. So in the light cone coordinates, this Klein-Gordon equation becomes this. X plus minus is equal x0, let's go, plus minus xd divided by square root of 2. And this is the, this one, in here, this is a d minus one-dimensional Laplacian. Then if we make an ansatz for the wave function phi, so that there is the dependence on, say, x minus has a plane wave form, then this equation becomes the Schrödinger equation. In other words, we can think about the Schrödinger symmetry, Schrödinger group, as a subgroup of the conformal group that preserve this ansatz on the of the wave function. So Schrödinger group in d minus 1 spatial dimension can be embedded. This one is a subgroup of the conformal field, this group of conformal group in the space in one time dimension, so d plus 1 space time dimension. At the level of the algebra, we can say the following. If you take this conformal group, so in order to get into this subgroup, we pick all operator that come in. To go from this algebra to this algebra, we pick all generators of the algebra that commute with one light cone momentum. Let's call that P plus. So you can do this exercise, take the conformal group, and then construct a subgroup of all operators that commute with a light cone momentum, and you look at the algebra that remains. That is the Schrödinger algebra. Okay. So then it is rather straightforward to at least write down a space-time that would realize the Schrödinger group. So if you want to realize Schrödinger group in D-1 spatial dimension, we can first realize this conformal group first. We know that it is the ADS space has this symmetry of the conformal group. So we can start by writing down the ADS metric. Okay, plus dx square. So how many dimensions we need? If you say we want to realize the case where this d minus 1 is equal to 3, then we will have to start, we have to realize conformal symmetry of 4 plus 1 dimension. So it has to start with ADS 6. Okay, so that is for them, there are four of this x1 plus dx2 plus dx3 square plus dx4 square. Okay. Or we can write it in the light cone coordinates like this: dx plus dx minus plus dx square. Now it's 3-dimensional dx square over. So that's it. That's it. Okay, this, since it is IDS space, it's realized conformal symmetry and it's realized the Schrödinger symmetry automatically, because this one is the subgroup of the conformal group. I'm sorry? P is equal to P naught plus PD over root 2. Something like this. P plus operator and the n, which map into n. P plus going to map into n in the Schrödinger group. So n is the central element of the Schrödinger algebra, and so P plus commute with everything. So P plus that we pick out, so P plus map into n. So there is a table where you can map, for example, the Hamiltonian map into P minus. In the light cone quantization, the light cone Hamiltonian is P minus. Okay. But this might this space-time realize more symmetry than we need. We can break the symmetry from the full conformal group down to exactly the Schrödinger group by adding one term into the metric that is the x square. And by trial and error, you can see that this one, this space-time actually has exactly the symmetry of the Schrödinger group. Okay. And you can first check that is that the scaling, non-relativistic scaling, is realized. So how does the scaling is realized is here. If we take only this piece, then it is invariant under the following transformation. You can rescale all the coordinates by the same amount. Okay, you can rescale all the coordinates by the same amount, and the metric, this part of the metric would not change. But this is the relativistic scale invariant. It is not the non-relativistic scale invariance where you scale time twice faster than space. So this the last term that we add here breaks this relativistic scale invariance. What it left is a combination of this transformation and the boost along the x plus x minus direction. As you recall that this part of the first term here is invariant also under the boost. Boost means that you take x plus go to lambda x plus and x minus go to lambda minus 1 x minus. Okay, so if you combine this relativistic scaling and boost, you combine them, you get x plus going into lambda square x plus. X minus is invariant because the scale and the boost factor cancel each other. And then this x plus going to this, and then xi going to lambda xi. And you see, you recognize here the usual non-relativistic scale invariance if one identifies the light cone x plus with time. So here this x plus plays the role of non-relativistic time. Okay, so this is how, this is one particular way one can realize the Schrödinger symmetry as the symmetry of a space-time, and one can hope that it might be a starting point for studying the holographic examples similar to unitarity fermions. So right now we don't have very good models that behave even qualitatively as the unitarity fermions, but we at least we have a space-time that realizes the same symmetry. Okay, let me stop here. There are a lot of recent developments, but I don't think I can summarize them. Thank you. Okay, so at the formal level, you can say you have a state, and then you compute the expectation value of that operator, and that is a characteristic, one of the characteristics of the state. So there are, each state is characterized by an infinite number of parameters, and only a few of them are important at the physical level. In particular, the stance parameter is important because it controls the first non-trivial, usually it controls the first non-trivial term in the operator product expansion. It is also important for other relationship that I did not have time to talk about. You can ask the question, what is the stance parameter in the quantum mechanical language, and that is the way that that it was introduced before. It is the characteristic of how frequently you find two particles at short distance from each other. Yes?
So in studying quantum mechanical system, it is often convenient to be able to go to Euclidean simulation space and by quick rotation.
Uh-huh.
And as far as the Hamiltonian is positive definite, one should be able to do that.
Mm-hmm.
The relativistic
Case.
theory, you can have holographic description both in Lorentzian signature and Euclidean signature.
Mm-hmm.
Now, for non-relativistic case that you are discussing here, if you try to quick rotate this geometry, you get a metric which is not real.
Mm-hmm.
Do you have a comment on that?
I have no, I don't know
So
how
in
to
theory,
do this.
quick rotation does not seem to be compatible the other hand, in non-relativistic conformal series,
Mhm.
I imagine you can do the weak rotation.
You can define correlation function in Euclidean signatures,
But
and
that's
they
not
usually.
described in the Euclidean rotated geometry. So why is it that you can do weak rotation in field theory side that you cannot do in the holographic?
I think, yeah, you weak rotate the x plus coordinate. The thing here, it might be related to the fact of why all this construction of this type doesn't give. Eventually, if you go to the phenomenological level, they don't seem to correspond to a nice non-relativistic system similar to unitarity fermions. The equation, if you write the equation, the Schrödinger equation in Euclidean time, it has the form of the diffusion equation. If the mass is positive, if the mass is negative, you have a wrong sign here. So in compactification with respect to x minus give you a spectrum of different components with even the sign of mass can change. It can be either positive or negative. And that's why the weak rotation doesn't work here. But in the case of unitarity fermions, we have only state with positive mass. There is no operator that carries a negative mass. So it is a deficiency of this construction that probably explain why they don't work that well. Yeah. But I don't know how to overcome this deficiency.
So there are no more questions. I think we should thank Son again for